before his venturing into engineering. Prior to his role at IIT Guwahati, Dr. Sir held a prestigious merit-based postdoctoral research fellowship at Swiss Federal Laboratories for Material Science and Technology, Zurich. During this period, he focused on innovative projects such as ferrimagnetic sky-mirror memory and development of biocompatible magnetic nanoparticles for controlled hyperthermia in cancer treatment. Dr. Dutta initiated his PhD work at Department of Electrical and Computer Engineering at National University, Singapore, where he awarded a fully funded research scholarship. Over the years, he has accumulated a remarkable body of work, including over 20 peer-reviewed publications in renowned journals such as Nature Communication, ACS Nano, Applied Physics Letters, and Nano Letters. His pioneering research on sputtered Bi2Sa3 has been pivotal in achieving high charge-to-spin conversion in topological insulators, paving the way for large-scale energy-efficient applications associated electronic devices. In 2020, Dr. Datta was awarded the prestigious Very Curie Postdoctoral Fellowship grant from the European Union Horizon 2020 program. This grant supported his research on amorphous ferrimagnetic multilayer systems, specifically focusing on hosting ultra-small, high-density, fast camera devices. His work has been well cited by peers in many international journals. His works have garnered over 380 citations by fellow researchers and, and a high H index of 10, which is remarkable for as early career researchers. Dr. Datta's collaborative spirit is evident in his transnational partnerships with national and international research groups, industrial collaborators, and renowned companies like RATE, GmbH, IBM, HCST, and CICET. In summary, Dr. Tanmay Datta's multi-facet contributions encompasses groundbreaking advancement in information storage and computing technologies, enabling an energy-efficient, data-driven society and for innovative energy and performance solutions. In biomedical devices, his work not only pushes the boundaries of scientific knowledge, but also helps in positioning IIT Guwahati and Assam as a hub for cutting-edge research initiative. Once again, welcome, sir, to this FDP, and we will be looking forward to have a nice interaction with you, and hopefully your talk will obviously enrich our knowledge. Thank you, sir.
Thank you so much. Thank you for this elaborate and such nice. It's so weird to hear about your work being spoken. But thank you so much for the nice introduction. And
I one more thing, we have a small felicitation for you.
Okay.
So I would like to.
But we'll do it at the beginning itself. Okay.
Yeah. Thank you, sir. Last is this for you.
Thank you. Good morning, everyone. Thank you so much for having me here, and thank you to the organizers for organizing this. Rashi ma'am for organizing all this and being constantly, coordinating all of this. I know it is a very difficult task to come at 9 a.m. in this weather and then attend this program. But please bear with me, and if any grudges regarding starting so early and all, I'm not to be blamed. It's all on the organizers, okay? So, the topic that I'm going to talk about today is on spintronic and quantum devices, and I think all of you are already aware of what the topic is, so you're very familiar with this. I have tried, probably I will not be able to cover all the slides I have here, so it's like 150 odd slides, okay? So they are too much, I know that, but I just kept it just in case if some discussion comes up, we will refer to them. My idea would be to, because you all are like all from electronics background, right? No?
Computer science, electrical, instrumentation, and physics, chemistry.
Okay, so it's a mix. Okay, that's even better because if it is a mix, then we have a variety coming in. So I have tried to keep most of the basic things in this field and not go too much deep into the devices, right? so that whatever interests you, if you are already working on that, that's already probably boring for you. But people who are not working on it, if you find something interesting, it might be helpful for you. You might seek more information on this. So that is my idea. For people who are experts in those things, my apologies. It is not very advanced. It is very basic. But I hope that I can, all of you can, at the end of this session, all of you have something new that you have learned here. That is my aim. Okay, so let us begin. This is already everything is mentioned in the introduction, but this is my own introduction that I was supposed to give. And at the end, I will also display again so my contact IDs and also so that if after this also any of you want to contact me, please feel free. I will also display this at the end of the talk. Okay, so going into the content. So this is the basic outline. So for spintronic devices, we will start with the basics of spintronics. Then we will talk about magnetic random access memories (MRAMs), both in GMR and TMR. We will, for those who are unaware of these terms, we will see what they are later. Spin transfer torque application and its applications, and spin orbit torque and applications, and some devices examples based on this SOT. Okay, spin orbit torque. So first is the basics. So the name spintronics. Here we harness, we manipulate, we play with the spin that is inherent to electrons, which is a basic property of electrons, right? And you are already aware that we have two kinds of spin that comes from electrons: the inherent spin, which is a quantum property, and then there is something which we call the orbital moment, right? That is basically the interaction of the electrons with the nucleus, right? And sometimes both of these spins can be used together, and therefore in that cases it's called spin orbit coupling. When the two spins, right, the two spins are coupled together, they are we get enhancement in these properties, and that's called spin orbit coupling. Okay. So in a classical sense, again, the spin, orbital spin comes from the movement of the electron around the nucleus of an atom, and the spin of the inherent spin of the electron, again, which is in classical way depicted by a clockwise or anti-clockwise rotation, and sometimes by an arrow which is south north or north south, right? So these are the two orientations. You can also refer to them as plus half and minus half quantum spin, quantum numbers. So whatever way you treat them, you will only have two different states of spin, and having these two discrete states of spin, or two possibilities of spin, gives us the ability to store information in the form of bit, right? So you have binary. We are generally working in a binary system today, and binary system needs two different kinds of states. So 0 1, okay, north south, plus half, minus half. These are all two different states, and they can be used to store information. So that is what is mostly harnessed in spintronics in terms of memory storage. However, the use of spintronics goes beyond memory storage. It is also in energy. It is also in biomedical. It is in sorry, in agriculture, in space applications. So there are many applications. Okay, but primarily so far the product level application of spintronics is in MRAMs, which is magnetic RAM, which is there in most of the new computers that come out today. The RAMs are no longer the SSD based RAMs we used to have earlier. They are mostly now coming into the MRAM form. Okay, so now I said that we play with the spin. So, but generally all our electronics is focused on charge, right? The binary for our in case of charge is 0 1, right? We have a plus and minus, or plus 0 or 0 1, right? So that is the binary we play with in case of charge based electronics, right? Or charge based transport that I say here, right? And many of you are already familiar what transport is. So the problem with charge transport is, as you know, that charge transport is always conducive to losses, right? It has the potential of loss, right? Because there are joule heating effects and all those kind of, or some kind of static or capacitive losses. So those kind of losses are inherent to charge-based systems. Spin-based systems, on the other hand, have the ability that you can have purely spin currents. I will show what a pure spin current is for those who are not familiar. You can have pure spin currents, and as a result, you can have zero charge current. And that, in an ideal system, would give us lossless transmission. However, that's why the keyword idle. It is not idle, nothing is idle. So we will have some losses, right? We will have some charge-based losses, but that will be very small as compared to a conventional charge-based system, right? So that's why spin-based systems have this huge advantage of energy efficiency, and that's why they are researched, or they are already in product development stage in multi ways. So in sensors, they are already there. Sensors are already made out using spintronics. Memory devices are already made using spintronics, and research is already on, and very advanced stage of product development is already on for healthcare, biomedical, for space technology. In fact, actually, space technology also products already exist. So spintronics has now evolved as a very good alternate for conventional charge-based devices. Having said that, charge-based devices still rule the world. They are the minority product, but eventually, and spin-based devices have a niche market. But at some point, I think it might change in the future, right? Okay, so as I said, pure spin current. So you can see there are four different kinds of current I have shown here. The first one is an unpolarized current. So you can see this current has equal number of electrons, let's say, or charge carriers, which have, let's say, up spin, and equal number of carriers which has down spin, right? So the total charge is 4 units of charge, but the net spin is 0 because the spin cancels out each other. Okay. When we talk about an unpolarized current, you see that there are two up spins here, one down spin. So three total unit of charge, okay, and 1 unit of spin current. Okay. Whatever is the differential. It can be the other way around. You can have one up and two down. That would also be a polarized current. Okay. Fully spin polarized current is when you have only one particular orientation of spin in your charge carriers, okay, as in this case. And here again, the total number of charge is 3, just like here, but the total number of spin now is 3, okay. Pure spin current is, as I said before in the last slide, that when you have this up spin moving in this direction, okay, and the down spin moving in this direction, your net spin current is 4 units of upspin, okay, but your charge current is 0. That is a pure spin current, and that is an ideal situation we want to be into. However, it is very difficult to reach there. We either operate in the polarized current or the fully spin polarized current. This is mostly the region where we are able to operate. Okay, this is very ideal, and I will just touch upon why it is an ideal situation. So we are all aware that electrons are subject to scattering, right? Wherever an electron moves in a conductor, it is subject to scattering. So we have always thought about, and we have known that scattering events leads to this kind of resistance, blah blah blah. But we never think, what does scattering do to the spin of the electron, right? The spin is also subject to change. So upspin electron, upon scattered, might end up being down. Okay, it might also be somewhere in the middle. That's also possible. And when I say middle, it and I am contradicting myself here, right? I said there are only two possible states, up or down. But now I'm saying it can be in the middle also, right? Any idea why? In the first or second slide, I said there are only two possible positions, plus up, minus up, down, north, south, right? But now I'm saying that it can also somewhere, after a scattering event, it might be in the middle somewhere. What do I mean by that? Okay, so I will give you what I mean by that, and this we will again come back to this in the later part, because this has to do with the quantum nature of it, right? In the quantum world, everything is probabilistic, right? And everything exists in a superposition of multiple states. So the two states possible are plus half, minus half, but the system will exist in a superposition of the plus half and the minus half state. So you can think of it as like A times up plus B times down. That is the superposition state that the electron will exist in, okay, in the quantum world. And only when you try to measure it, it will settle down either in up or down, because it will collapse into one of the states. So when I say it has only two possible quantum states, it means that it will only collapse into either of these states, okay, but it will always exist as a superposition of multiple states. And that's what I mean when I say that an up electron might also end up somewhere in the middle on being scattered, okay. So that is the reason, because of this random scattering events that might take place, it is very difficult to have a pure spin current, okay. It will be a totally different thing if you are talking about the superconductors, because then the scattering goes away, right? We have all those Meissner effects, and because of which you have Cooper pairs and all those things. So, but in a conventional conductor, you will have scattering events. Okay, so magnetism in materials. Okay, so when we talk about magnetism in materials, what I refer to is how does magnetism or spin manifest in material form. Now, we all think about magnets, right? When we talk about, when we talk about magnets, what comes to your mind? On this, I want some answers. What comes to your mind when I talk about magnets? If I just say the word magnet, what comes to your mind? Attraction, repulsion, maybe a horseshoe magnet, maybe a bar magnet, because this is what we all have seen in our schools, in our colleges, even who are not working in any of these fields, we would also know about this, isn't it? So that's the thing we think of, right? Now, we also think probably of, I don't know, like some iron bar or this kind of things, right? So, how does this spin or magnetism manifest in materials? It manifests in multiple forms, but the most common form that we as a society or we as humans interact with are the ferromagnets. Okay, so the ones that we generally refer to as magnets are ferromagnets. Okay, iron, okay, cobalt, nickel. These are the three most commonly at room temperature available elements, pure elements, which exhibit ferromagnetism at room temperature. Okay, so they are the ones through which mostly the magnets are made. Uh, you all have played with this bar magnets, no? Small scale, right? Cylindrical, correct? What are they made of? I'm pretty sure all of you have seen them. All of you have at some point hold one of them. What are they made of? They are generally made of alloys of iron with some rare earth metal. Okay, but mostly iron content. Yeah. Some rare earth metals are used there to make them more strong in magnetism. Okay, the ferromagnetism is enhanced. They become stronger magnets. And the reason again goes back to the second slide. I mentioned something about spin orbit coupling. Okay, so again, I'll not go to the details, but I'll just say why. Okay, so what happens in a ferromagnetic material is all the magnetic units, let's say. Now I'm consciously referring to the word magnetic units instead of saying electrons. Okay? Because when I say electrons, there are billions of electrons in a small piece of material, right? Now, are all of these electrons contributing to this magnetism of this material? The answer is no. Okay, some of them will contribute, and mostly the ones are not that are not free, mostly that are bound will contribute to it, right? But anyway, point is that now we refer to the smallest unit we refer to is the magnetic unit, and it's called a magnetic moment. Okay, magnetic moment, that is the smallest unit we refer to, and we consider that as small m here. Okay, the small m is the magnetic moment, and in this diagram or this picture, everything has been every moment is represented as an arrow. Okay, and you can see all the arrows are pointing upward in a ferromagnetic material. Okay, which means that all of them will either point up or north or down, that is south, right? In any particular given at particular given moment. Okay, so if you switch it from one to other, they will switch from north to south. You can have to apply very strong field, you can switch its orientation, but otherwise it will always, but it will in any situation it will always point in one direction all the moments. In ferrimagnetic, okay, I'm sorry for this mess up here, the text is not seen. This is a ferrimagnetic material. The difference is a O and a I. Okay, this is a ferromagnet, this is a ferrimagnet. In a ferrimagnetic material, you can see some of the moments are smaller in length, so the amplitude is low, and also they are opposite in direction. Okay, so the small m is not only m, it is m1 and m2 now, and they are non-zero. Okay, and the total m is also non-zero. So that means capital M is the total M. Okay, here also capital M is the total M, and it is non-zero. Here also it is non-zero. But you can understand that the opposite. If you think of a crystal, each layer of that material is having opposite spin, something like that. Okay, they are opposing each other. So that's a ferrimagnet. And then you have antiferromagnets. Antiferromagnets are a very hot topic, especially people who are from the physics background might already be aware. It's a very hot topic, antiferromagnets, again because of their very fast transitions, low dissipation in transport and everything. What happens in antiferromagnets? These moments are all opposite to each other, right? And the net magnetism, the total capital M of in this case is zero, unlike in ferro and ferrimagnets. Okay, here because they are equal in amplitude, so they are opposing each other, they cancel out each other, so the total capital M is zero. And then are the paramagnetic materials. There are many materials which will exhibit some kind of magnetism or magnetic properties, but only when a huge magnetic field is applied, right? When at least few tens of Oersted of magnetic field is applied, they will align. So here you see they are all random. The magnetic orientations are random. Okay, they are randomly aligned to each other. But when you apply a very strong magnetic field, you might be able to align them. So they are paramagnetic materials. What I have not shown here is the material that is mostly or the kind of magnetism that is exhibited by almost all the or majority of the things around us is called diamagnetism. Okay, diamagnetism. So most of the material we see, even this is diamagnetic, except the electronics inside, right? The metals you see, even copper or many things you will see around us, they are all mostly diamagnetic. Okay, and they do not find application in spintronics. Diamagnetism does not find application in spintronics. That's why I have not mentioned here. But these four kinds of magnetic materials, they find application, but they are few. The most of the items around us, their magnetic response to a magnetic field is diamagnetic in nature. Okay, I will not go into the details of how the how this response is in response to a magnetic field and all, but I hope that I have been able to at least give you an idea about how magnetism manifests in materials. And here I'm showing you this MFM images. So this is magnetic force microscopy, and this is just to give you some idea that we all talk about magnetic domains. I'm pretty sure all of you have heard about magnetic domains, right? Magnetic domains, this is how they would look under a microscope, a magnetic force microscope. Okay, so these two different colors, yellow and orange or yellow and brown, as you see it, are two different orientations of magnet. So in the brown regions, the spin is in one orientation. In the yellow regions, the spin is in another orientation, or the moment is in another orientation. Okay, so this is the manifestation of magnetism in materials around us. Okay, now these are the materials that we use for all our day-to-day spintronic work. Okay, these four categories of material. I will quickly mention that this is an inherent interaction called the exchange interaction between two adjacent spins. If two spins are placed near to each other, and when I mean near means at the atomic scale near, okay, they interact with each other through something called the exchange interaction. Okay, and this exchange interaction can make them pull each other or push each other. That means it can be ferromagnetic, it can be anti-ferromagnetic. Okay, it can be making them align parallel to each other. It can also make them parallel, anti-parallel to each other. Okay, there are other kinds of exchange interaction also, but let's not get into that. But what I can just say now is that this is the interaction that forces, or that is the genesis of magnetism in materials, because this makes the spins align either parallel or anti-parallel to each other. Okay, so this is the most inherent interaction that happens. By the way, please you can stop me whenever you have some questions. Yes, please.
Sir, regarding that ferromagnetic, you have said some amplitudes are small. How is that possible?
This one.
Yes, sir.
It is possible because, for example, I gave you three examples: iron, cobalt, nickel. These are at room temperature ferromagnets. That means they are all aligned in the. I have not given you any example of a ferrimagnet so far. Now, what happens is with iron, if I mix an element, for example, gadolinium, it's another element, right? And gadolinium doesn't show any magnetism at room temperature. Only at low temperature, it will show some amount of magnetic properties. Okay. Now, when I mix this element with iron and I make an alloy called iron gadolinium, what happens is iron is in one of the layers, let's say crystal. If you imagine a crystal, in one of the layers you have iron, in one of the layers you have gadolinium. Okay. So iron and gadolinium, but iron is, let's say, pointing in this direction, gadolinium will point in this direction. Okay, but iron has this magnetic moment, the amplitude, let's say of 2 Bohr magnetron. The unit here is Bohr magnetron. Okay, so let's say it is 2 Bohr magnetron. Gadolinium probably will have 0.5. It's an inherent property of gadolinium.
These magnetic moments are coming from electrons.
Yes. So electrons give rise to this magnetic moment, right? And that's what I said, that now I will not talk about one electron. I will talk about one unit of magnetic moment which is arising from electrons. Okay. The electrons are generating this, but I will come like to a bigger platform and you treat each unit as one unit of magnetic moment. Inside that there are electrons which are giving rise to this magnetism. Okay. So it is because there are two different materials, they have two different moments. That's why the amplitude is different. So if you have any other questions so far, please ask, or I can move ahead. It is, see, I am faced with the same situation that you are faced in the class. I know that, right? When you are here and you are asking the same thing, that you have any questions, I am also there. So please help me out. You will understand my situation. I would be better able to communicate to you if you are communicating with me, right? Even if I cover 10 slides today, I am happy with that. But I just want that whatever I communicate, at least I communicate something to you, and you can receive something. That's my aim. Okay, so please feel free to stop me. It's fine. I am happy to just cover 10 slides today. That's okay.
What is the M, small and capital M?
Sorry?
Small and capital M.
So small and capital M is the so each unit of magnetic unit, every moment. Okay, you can imagine. Let's say for imagination, each atom I take as one magnetic unit. Okay, and there are electrons inside it. So I take each atom as one magnetic unit. Let's say so one magnetic moment. So that is the small m. Okay, and when I take a cluster of it, that is capital M. And this is the same capital M that you measure in our 12th physics classes. I think most of us have taken that. The capital M, the magnetization that we talk about, that capital. Okay. So it's a per unit volume, capital M. No? Okay. Fine. So I will probably skip through these things. Probably this will be boring for you, and maybe will not have much implications here. I will just show this one. So many of you probably are familiar with this thing, no? Hysteresis loop. In electrical we have this, in electronics we have this, physics definitely we have this. So hysteresis loop, I think many of you are familiar with. And what happens here is that when you change the magnetic field, this is the magnetic field H. With the change in the magnetic field, this capital M that you just now asked, the capital M, the magnetization, it doesn't follow the same path in either direction. When you go this way, or you come from positive to negative field or negative to positive field, the path is different. Okay, so for example, this is the arrow, you just follow the arrow. If I start from a negative field and I go, my magnetization is tracing this path. Okay, but when I come from the positive field to negative field now, positive edge to negative edge, I will follow this path rather than this path. I mean, not I, but the material, right? So that means for any given field, let's say I take any field here, there are two states of magnetization that are possible, correct? So that gives us the possibility to store information in these materials, right? This is the same, this is a very basic principle on which our phones, our computers, our memory, hard disks, everything operates on. They rely on hysteresis. Depending on which path I take, the state will be either a plus m or a minus m, right? That means I have two different states. Okay, so hysteresis is important. Huh? Okay, I will now go into this one, which is called a MRAM. I had told you that this is a device that is already there, it exists, and it's a replacement for the conventional RAM that we already have. People from electronics, computer science probably already are aware what a RAM is, and you have already probably taught this, so you know in detail, right? Now, what is a MRAM? It's a RAM which has a magnetic aspect to it. Okay. Now, what is the magnetic aspect? What do you think is the magnetic aspect? why do I why do I need to use this magnetism here and replace the conventional RAM? You can just float ideas like that. Imagine we are in a brainstorming session today. We want to develop a new product. Okay, and we have RAM. We are all familiar with RAM. We know what a RAM does. Some of you are more familiar than me. But then, why do I want to replace that with something that is magnetic? What benefit do I get from that? What is the advantage? At a very fundamental level, what is the problem with a RAM? With the conventional RAM that we have? Fundamental level, not at the circuit level. Don't think at the circuit level or the architecture level. Think at the device level.
Conventional RAMs are more volatile as compared to NVMe probably.
Sorry, can you be a bit louder?
Conventional RAMs, that is dynamic RAMs, are more volatile as compared to.
Exactly. So the key word there is volatility, right? So the key, I know your voice is you have throat issue. Sorry, I did realize when I asked you. So volatility is the issue, right? RAMs, the conventional RAMs made out of silicon-based devices are volatile, correct? That means to store information, to retain that information, I have to constantly either keep it energized or periodically, if imagine it's a capacitive leakage, I need to periodically keep recharging it. Only then that information can be there. Otherwise, at some point it might go away. Right? So that volatility is an inherent problem with the conventional RAM. So that's where magnetic RAM comes in, because magnetism inherently has non-volatility. That's what I just showed you in the hysteresis loop, right? It has non-volatility. It can store your information. So you see, I'll just go back to this hysteresis loop again. See, let's say your information is stored in this form. That means a plus M, let's say. Okay. So somewhere here, let's say. So you have applied a magnetic field. You have stored this information. Now you take away the field. Okay, you take away the magnetic field. This material will go and rest here. That means it still has a nearly the same capital M as it had when you applied the field. Okay, it is here. If you remove the field now and forget it about for years now, it will still remain here, isn't it? It will still remain here. The day you want to go into that material of that bit and find what is the information stored here, it will show you this value, it will not show you this value. Correct? Because both these states are possible at zero field. But you have taken it to this area or this region and then left. So you have applied a positive magnetic field, left it, so this is what is the memory retained here. Okay. After few years you check, it will show you the same value. Right? If you want to switch it from this value to this value, you have to apply a very strong opposite field. You have to take it here in the opposite direction, apply a very strong opposite field. Then only when you release it, it will come. Right? That means, in terms of physics, if you talk about it, there is an energy barrier. It's like a hill, it cannot cross it. It has to be given enough energy to go and cross over that hill, right? So that is magnetic hysteresis, and that magnetic property, that memory retention or hysteresis property of that inherently comes in magnetism is used in MRAMs. Okay. So this is a schematic of an MRAM. So let me just show the first one first. So I don't know if you are able to see from the last. Do you see there are three different layers here?
Yes.
Okay. So the three different layers here. The top layer is called the free layer. So it has a red and blue arrow. That means it can be in this direction or it can be in this direction. It can be in north, it can be in south. Okay. The middle layer is not magnetic. Okay. It can be a metal, it can be an insulator, but it is not magnetic. The third layer, the bottom layer, that only has a white arrow and it is in one particular direction. You may not be able to see the direction from there, but it is pointing in this direction. Okay. So what that signifies is this layer is called the pinned layer. Okay. It is pinned. It is not free. It cannot change its direction. It is pinned. Okay. The top layer is free layer. It can go this way, this way, this way, this way. That means it can store information, right? It can store information when it is in here. So let's say 1. If it is in this direction, it is 0. Right? Now, what do I need to do? All I need to do is do something so that I can change it from 1 to 0 whenever I want. Right? That is the write operation. Right? And the second is to read it. I need to be able to read that it is in 1 or in 0. That's the read operation. So these are two things I need to do with this device. You agree? Okay, fine. So the writing method I will talk first. So the writing method is, there is a bit line here which is schematically shown. Think of it is like some kind of a miniature field generator, okay, magnetic field generator, some kind of a coil, let's say. It generates a very small magnetic field, okay. It generates a very small magnetic field in the vicinity of this device, okay. And that magnetic field, depending on the current direction, you can change the magnetic field direction, isn't it? And by that, what you can do is you can switch the magnetism from one direction to the other, right? You on the right line, you on the circuit, current goes, apply the magnetic field, switches it, right? Again, you want to switch it back, change the current direction, it will switch it back, right? Like this. Okay, makes sense? Now that is the right operation. How do I read it? That's the more interesting part. How do I read it? How do you read it? It's simply a magnetic material. It has it is either in the north direction, south direction. You can imagine up, down, whatever you want. But it is either in one direction or the other. How will you read it? How do we read a charge-based device? In case of a charge-based device, how do we read it? Transistor, for example. How do you say it's on or off? You probably are sensing something. What are you sensing? You can either sense the voltage or you can sense the current, but something you have to sense, no? How will you sense this? So how we sense this is by using, any ideas? Okay, so I will tell you how we sense this so far. Maybe there are some other ideas we have not explored yet, but so far how we sense it, I'll tell you, is by using a principle called GMR or TMR, which is giant magnetoresistance, GMR, okay, and tunneling magnetoresistance, TMR, okay. We will have a look into in some slides about those two things, okay. But the word magnetoresistance, see, when you are measuring V and I, you are eventually also measuring resistance of something across something. Similarly here, you measure those voltages, those currents, and you find out the resistance. And the resistance is magnetoresistance. What I mean by that is that the magnetic state will influence the resistance. Okay, so it's called magnetoresistance. So it is different from charge-based devices in that way that here we are concerned about magnetoresistance. We are not taking any break, like it's 3 hours or we'll take a break. 10:30 will take a break. Okay, fine. So this is the principle of magnetoresistance is used to sense them. Okay. Now there are three different kinds of them. Okay. One is called field switching MRAM, because I told you the switching is done by applying a current and that creates a magnetic field. It switches it. This is a non-contact mode. So you can think that the device doesn't need to come in contact with the current line that is generating the magnetic field. Okay. It can be non-contact mode because magnetic field is non-contact. It has action at a distance. The second one is called STT switching MRAM. Now this is another term here. STT. STT is spin transfer torque. Okay, spin transfer torque MRAM. Here, the switching or the writing is done by spin transfer torque. We will discuss it on another slide what that is. Okay. The third one is SOT switching MRAM. So here, the writing mechanism is spin orbit torque. Okay. So in these three MRAMs, the reading method is still the same. The writing method is changing. The first method is field based. When a current carrying coil generates a magnetic field, this is spin transfer torque STT driven. The third one is spin orbit torque SOT driven. Okay, so these are the three different kinds. Currently, what we are already using in our computers is the middle one, STT. Okay, spin transfer torque switching MRAM. Let's see what happens here. Okay, now we will first talk about the left hand side is the write mechanism, or kind of read also, but the right hand side is definitely the read mechanism. Okay, the right hand side is GMR, giant magnetoresistance, or in some cases you can make it TMR, that is the tunneling magnetoresistance. I will tell you what the difference is. So you see here there are three layers just like before. Two magnetic layers in gray, one green layer which is non-magnetic, and it is generally a metal which is copper, chromium, like that. Okay, so the green one is a metal. Now what happens is when electrons are passed through through this stack from this direction or that direction, electrons are scattered. This star mark thing, these are scattering events. Okay, they are scattered. Okay. Now, what is the difference between the two diagrams? If you observe carefully, here both the magnets are in the same direction. Ferromagnet, right? Ferromagnet, yes. Both are ferromagnets and both are pointed in the same direction. Okay. Now, this in a real world, this is a thin film of maybe around 3 to 5 nanometer thickness. 3 to 5 nanometer thick film. Okay. This one. This is also around 5 to 7 nanometer thick. Okay. In middle we have around 2 to 5 nanometer metal. Okay. Now what happens is when the current is flowing in either of the directions, scattering takes place. As I said, scattering we all again know resistance, right? We all know scattering will lead to resistance. Now what happens in these layers is something called spin dependent scattering. That means the scattering is not general scattering. The moment there is a magnetic material, the scattering becomes special. It takes into account, before the electron is getting scattered, it takes into account what spin it has, or what spin is there in front of it. That determines how it gets scattered. Okay, so schematically how we are showing it is like this. See, when both of them are in the same direction, both the layers are in the north direction, and see, these are not individual movements, these are layers. One layer, two layers. Both the layers are individual magnets, and they are pointing in the same direction. When that is happening, the current that is flowing through them will have both the upspin and the downspin. Maybe the upspin is blue, let's say, is here. No? Upspin is blue, and the downspin is the red. Okay. See what happens. The upspin doesn't get scattered. It goes through in both the layers. It is like that there is a gate here. There's kind of gates here, and the gates, the security guards at the gate have this preferential treatment for their kind of people. Okay, we all think about people, caste, divide, all those things, right? So let's think like that. You are my category, you are my caste, you are my this, you are my friend. I will let you go. Okay, you don't belong to that. I will not let you go, or at least I will put a resistance for you to go. That kind of a thing. The electrons also have this kind of preferential treatment. The people they like, or the electrons they like, they will let go. The electrons they don't like, they will scatter them. Okay? So you see, this upspin will easily go through. Okay? They are not getting scattered. Okay? The downspin, this is getting scattered because the black ones, this moment here, or this direction here is up. They don't like the red one, right? So it is getting scattered, but the blue one is getting through. You look at this diagram here, one is in this direction, one is in this direction, right? So what happens? One is getting scattered at this edge, the other one is getting scattered at this edge. That means both of them are getting scattered, right? So which one will have more resistance? Which one will have more resistance? Second one, obviously, right? So the second one has higher resistance, the first one has lower resistance. That means by changing the magnetic state of the layer with respect to each other, I can have different resistance states. Right? Correct? So that is called giant magnetoresistance. Okay? Now, this is the sensing mechanism. I told you this is a sensing mechanism, right? So if I pass a current just like this, if it is in the same direction, both the layers are in the same direction, my resistance is low. If they are in the opposite direction like this, my resistance is high. Correct? So that is how by passing a current I will know if it is in the same direction or the other direction. So that means I can read my bit 0 and 1. Yes or no? Yes? I can distinguish. Correct? How do I write it? I told you one mechanism is a spin transfer torque. Now the same mechanism is used here, you see. The same mechanism is used here. These are in two different directions. But if the current is higher, if I increase the current, I have a sensing current and I am measuring the resistance. Now imagine that same gate analogy if I think of, right? Two people, three people coming at a time, the guard can chase away some people if he doesn't like. However, imagine there is a mob, thousands of people coming. What will the guard do? He will join them. He will say, I am also with you. Right? I'm scared of my life. Right? General, every human will do that. That's what is happening here. So the moment many electrons come together, right? You increase the current, many electrons come together. They force this one, which is not in the direction, which is not aligned with the pin layer. Is the pin layer? It is not aligned with it, right? It will change it. You join us now. Okay? So same sensing mechanism sensing mechanism. So the same sensing mechanism can be used for writing also. And this, you can imagine, it exerts a torque. So one electron is coming like this, let's say, just taking one electron or one moment at a time, not electron, one moment at a time. One moment is coming like this, and in the layer, let's say it is like this. It will come and try to change it. Okay. Second one again, push. Third one, push. Fourth one, push. Eventually, it will come like this, right? So that means this is applying a torque, right? And it is transferring the torque. It was like this, it is coming, it is trying to transfer its torque to this one, right? So this is called the spin transfer torque. Okay, so that's why the name STT, spin transfer torque. Okay, I hope I have been able to explain to you how this operates. Okay, right. Okay, next is I think this one. Yeah. Okay. So now I told you about GMR here, right? I described about GMR. I told you there is another sensing mechanism which is called the TMR, tunneling magnetoresistance. Okay. In that case, what happens is that the in the middle that metal layer that I had, the green color one, that is now replaced by an oxide. Okay, maybe silicon oxide, aluminum oxide, silicon nitride, some kind of an oxide. Okay. Now, what does an oxide do to a flow of current or flow of electrons? It blocks it. An oxide will block it. Correct? Correct? Insulating. Correct. It will block it. In terms of physics, it presents it with a huge barrier. That means that the energy barrier that it is now facing is huge. Like in semiconductors, we face few EVs. Here it is even higher, right? So the electrons cannot pass through. Right? The electrons cannot pass through. It is not allowing it to pass. However, look at this analogy. It's like a dam. It is preventing the flow of electrons. That means the flow of water. Okay, but some of the water can seep in through. Okay, and pass. Okay, if you leave it for enough time, you will see some water somewhere seeping through. Small droplets might just come. Right? Not the entire one will come, but small droplets might come. That is called tunneling. That means it is not crossing the barrier like this, but it is simply seeping through a tunnel. Okay, so that's tunneling. So whenever the same sensing mechanism, as you see here, is done with the oxide in between, that is called tunneling magnetoresistance, because the same magnetoresistance will be there. I discussed how the magnetoresistance comes, right? The same magnetoresistance will be there, but this time it will be tunneling dependent. Now, why? I'll just give you the reason why. I mean, why did we come from a GMR to a TMR? So GMR was first developed in the 90s, and then we came to TMR in early 2000s. But why did we come from a GMR to a TMR? The reason is tunneling. When you use tunneling, the sensitivity improves manifold. It becomes very less susceptible to any ambient noise. Okay, any disturbance, any thermal fluctuations, it becomes insensitive to that, and that is why the same magnetoresistance that I was measuring before with a metal in between, I am now measuring with the oxide in between. Okay, and it makes my devices better, more sensitive, noise proof, and so on. Okay, so that's why a different mechanism is used, but similar. Okay, magnetoresistance, but tunneling magnetoresistance, and same MRAMs are now developed with tunneling magnetoresistance. Okay, so the red one is an oxide now. Okay, this probably is an animation. I don't know, it will not play, I think. Let's forget about it. So anyway, I mean, people actually got Nobel Prizes for this discovery because it was a discovery of kind of the century, and it revolutionized everything in every field. So they got Nobel Prizes for this. Anyway, talked about giant magnetoresistance already. What I will do is now I will move to this I will skip. This is another animation simply showing what happens in a GMR, right? The same scattering thing. When they are opposite to each other, you see they're getting more scattered. when so and here you see when enough current starts to apply, they can also switch. Okay. So this we have already discussed. Now let me come to something called sorry, this should have been before. Let's keep this. I already talked about tunneling magnetoresistance. Okay, so this slide maybe I'll just discuss something. So here you see, you understand it is a density of states, right? So ideally a density of state diagram would look like this, correct? But you see here the density of states for the upspin and the downspin are different, right? Because the density of one in a ferromagnet, the density of one is more than the other, right? You have more upspin or downspin, right? They are not in equal numbers like in a metal or in non ferromagnet or non-magnet. Okay, so the density of states are different, and when they are tunneling across, no, you see again the same thing here. This one upspin up, both are up, both the layers are up, so the electron goes through, the upspin goes through, the downspin is getting scattered. Here both the spins are getting scattered because either of them are opposite to each other, right? The same thing, but here the density of states is also shown because the tunneling probability, the probability for that electron to pass through, right? How easily can it pass through? Well, it's not easy to tunnel in the first place anyway. It's a huge thing. But how much or how many of them tunnels through, that depends on the density of states. And that's why this density of states is shown. I just leave you with this comment that on either side, if the density of states of the sending and the receiving side are similar, then they are scattered, they are tunneled without scattering. Okay. If the density of state on both sides are different, then the tunneling also reduces. As simple as that. Okay, because the density of states on both sides are similar, right? Tunneling is easier. Density of states on both sides are different. Tunneling is difficult. Okay. Okay, so I will leave this probably STT. Okay, so yeah, maybe I'll just talk about this one a bit. So here you see there are we have only talked about three layers so far. This reference of three layer, okay, the reference layer, the free layer, and the barrier in between. Okay, this is the three layers we talked about so far, isn't it? We did not talk about any other layers so far. But in reality, there are at least 5 to 10 other layers. Okay, here also I'm schematically only showing 3, 4 more layers. But there are other layers also which are needed, and these are needed for multiple things. So, for example, this reference layer or the pinned layer is pinned. The reference layer is the same as pinned layer. Okay, don't confuse; they are the same. Now, reference layer is being kept at reference or pinned by this structure. Okay, the hard layer and ruthenium. What they are, I will not go into that. Okay, but some other layers are there which is keeping the magnetization of this fixed. Similarly, there is something called a seed layer and a free layer, and all these layers have different purposes. Some of these layers, like seed layer, for example, is there so that the crystallography, the crystalline structure of these films are well. Whatever I want, I can grow it like that. Okay. So these are all grown with thin film depositions. Some of you may already have heard about techniques called PPD, CPD, MB, ALD, right? So most of these are grown by these kind of methods, right? Mostly sputtering PPD and PPD is used here. But there are multiple layers basically, that's the message, and all these layers have their own function. Okay, other than the three layers that are discussed, because these are the technologically important and active layers. But there are other layers which are also in a supporting role, and without the supporting stuff, this main people cannot operate, right? So they are also there. We have to keep in mind that thing. Okay. Okay, so here I will spend a few minutes here, not few minutes, just a small glance here. So I just wanted to tell you that or show you that material development is also a very important part in development of technology. At least at the in the micro and the nano world today, especially in nano world today, it has become more difficult and more important to have knowledge of material science to develop new materials, use them, engineer them as we need it, right? So here two parameters I'm showing. So one is called the damping parameter alpha, and the other one is called the anisotropy parameter. Okay, these are parameters of a magnetic ferromagnetic material, let's say. Okay, as simple as that. What they are, let's not get into that, but damping probably you can understand very easily is that anything that damps, right? Damping parameter. So if the damping parameter is high, it is damping something. Okay, what it is damping is, it is damping the oscillation of the electron. So the spin I told you is up, okay, but if some energy is there, that means it is not at 0 Kelvin. Some energy is always there, no? It will always try to move like this. Okay, if you can imagine, right? It is not stable like this. It is moving like this. Some ambient energy, it will always be there unless we are at 0 Kelvin. So because of that, it is moving like that. If the damping is high, if the damping parameter is high, this oscillation is damped. So the oscillation is very small. If the damping parameter is low, it will oscillate like this. Okay. So that is the difference between high damping and low damping. Okay. The anisotropy is basically gives us the measure of how strong the magnet is. That means how difficult it is to change its state from north to south, 1 to 0, up to down. Okay. The higher the Ku, the higher the anisotropy, Ku is the anisotropy. Higher it is, higher is the stability. My information is stable. Okay, so that's why this factor is there. See, delta. Okay, delta is the thermal stability factor. It is called, and it is basically a ratio between the Ku here, right? The Ku times the volume divided by the kVt. Kv is the Boltzmann constant. All of you are familiar with. T is the temperature. Okay, so higher the temperature, lower is the stability. That's why you must have seen in those movies and all. Whenever you want to destroy some information, what do? All those criminals, no? They show when there is a some police raid, ED raid, or whatever raid. What do they do with the hard disks? What do they do with the pen drives? Huh? Either throw in the fire or put in the microwave. Right? You have seen those, no? So the reason is that higher the temperature, lower is the stability. You increase the temperature, the information is lost. Okay? So our idea is to make this delta higher so that we can store the information. So therefore, delta higher means we want Ku effective to be higher. That means we want materials which have higher Ku effective. Okay, and we want the T to be lower, but T is not related to the material. T is related to our own ambient temperature. Right? So only thing we can do about is we can change the Ku. We can make it higher. So we go for higher Ku material to make more stable devices, information wise stable. Okay, that means they retain the information. I buy a hard disk, I have a guarantee. Generally, they give a guarantee for 10 years. So data retention time we want at least for 10 years. My hard disk should store that information without failure, right? Or my RAM should be able to store that information for 10 years if I don't change it, something like that. Okay. Alright, so material development point here, and wherever I want, whenever I am making a sensor, no, like a GMR sensor, GMR is a sensor, TMR is a sensor, I showed you. If I have a sensor, okay, the sensor I want low K, okay, because the sensor has nothing with data retention, right? Sensor doesn't store information, but what I want in the sensor is that it can easily sense which direction something is. So if my Ku is very high, my sensor will only be able to sense one thing, not the other thing. So I need the sensor, in the sensor I want the Ku to be lower and the damping also to be higher. I don't want this. I want it to be like this. Because if it is like this, there is a chance that it can go like this. Because sensors are because the Ku is already low. The KU is already low. If it is moving so near to the other direction, at some point it will just switch. I don't want that. That's why I want in sensors, GMR, TMR and all, I want the KU to be low, but I also want the damping to be high. So then my movement will only precess like this, not like this. Am I able to explain? Okay. If you have any questions, please let me know.
Sir, KV is not dependent on density.
KU is very good question actually. It is not directly, but the moment I change the material, they are interrelated. No? It's a material property. So that's why the search is. That's why that map. So if I want high KU, low damping, or sorry, low KU, high damping somewhere here, right? If I want high KU, then somewhere here, right? So that's why that map. But it's a material property. It will be interrelated. Okay. Right. So I already talked about these three different kinds of FRAM. So I talked about the field-based one, STT one, and SOT one. I have not spoken about so far. So spin orbit, torque, and application now. Okay. What is SOT? So far I have told you that to the right mechanism in STT is that when the current is flowing, it's like huge number of electrons coming. It is changing the direction of the magnetism in the desired layer. Okay, that was the mechanism in STT. It is transferring the torque. Now, when we started to work with these devices, we found a problem. Maybe you are not able to see it at this point, but let me tell you, what happens is the read and the write mechanism is similar, isn't it? In that STT. The read, when I pass a small current, I face a resistance, and by seeing what kind of resistance I have, low resistance or high resistance, I know the state of it. Correct? That if the layer is like this or layer is like this, right? Now, I am passing higher current, then I am able to switch. Okay? That means the read and the write method are same. Only the current amplitude is changing. Correct? Now, what damage it can do is, it can have unwanted change in the magnetic state sometimes. Right? Second, when I'm passing this huge current, that can damage my device. Because writing means needs more current. More current means there is a probability of my device heating up and getting damaged. Because I told you stability is inversely proportional to temperature. Isn't it? More current to write can also mean more heat generated. More heat dissipated or generated means less stability of the information. Right? So that means it has an inherent problem that when I'm trying too hard to switch it by passing more current in STT, it might damage my device or at least corrupt the data. Correct? So we came up with a different mechanism, and that's called the spin orbit torque. Here you can see the read mechanism is the same as before, is across. Okay, across these two terminals I read the resistance and I know what is the state. Is it both are parallel or they are anti-parallel? Okay, read mechanism is the same. The write mechanism, the write current is no longer passing through the junctions. The write current is now only passing parallel to the free layer. Make sense? Okay, I'll repeat that again. Earlier, the write current and the read current both went through in this direction, top to bottom. In this case, you see the read current is still in this direction. Okay, but the write current is not passing through the junctions. It is only passing parallel to the intended free layer, the layer that I want to change the information. Okay, are you able to follow now? Yes. Okay. So that takes away the problem that I just now said, right? Because the read current was never the problem. The read current is small, doesn't matter. The write current was the problem because the write current was so high that it would heat up the battery, heat up the device, corrupt the information, and sometimes it may damage the device. So the solution found was using a different physics altogether. Instead of using the spin transfer torque, we started using the spin orbit torque. It's another torque, but the torque is like this. So earlier I told you This is, let's say, one, the electrons are coming and trying to switch it. Okay, spin transfer term. Now this is different. Now the electrons are passing like this. Okay, just by passing like this, they are trying to switch it. So, for example, when I'm passing in this manner, maybe it will not change because both are in the same direction. Now, if it is like, if the spin now is in this direction, so every electron that is passing, okay, and it has a spin in this direction, it is trying to influence it, but not like this. But by going near to it, it is trying to change its direction. Okay, so this is spin orbit torque. Okay, and my students actually came up with this analogy, and this is, I did not think of this analogy. I'll show you this analogy somewhere down later. Okay, I'll come to that analogy. But you remember the story with this what is it called Mangalyaan? ISRO had this Mangalyaan. No, I think a movie was also made, Mission Mangal or something, isn't it? So there they use this, and the reason they were able to do it at 1/5 of the cost of NASA was that they used the gravitational field of Earth itself to use it like a slingshot. Correct? They made it orbit like this again and again, increasing the orbit every day, and then finally released it. So it went like a slingshot, right? So they harness the energy from the Earth's gravity. Similarly, here also it's like that. I mean, this is an analogy, okay, nothing to do with gravity here. But these ones that are going near, no, they are also making some kind of field here, nearby field. Huh? And that field, every passing one is trying to change it in that field. Okay, and at some point, it just will flip. Okay, so it's a non-contact. The electrons are not passing through it, but it is passing near to it, and it is kind of that the field it has in. And again, no, this is, I'm using this analogy, or I'm talking about this field in a totally inaccurate manner, just for understanding. Okay, this is not physically accurate, whatever I'm saying. Okay, it is just for understanding how I'm trying to explain it. Okay, and that is where the spin orbit coupling comes into play. So this spin that it has coupled with the orbit, okay, and that spin orbit coupling makes this happen. Okay, so we should break now. Okay. After this, I will talk few more minutes about this one, and then I will explain how this action comes into play. Okay, and the action, the way it does is through this thing called spin Hall effect. You are all familiar with Hall effect, no? Hall effect, all of you are familiar with, right? This is the spin Hall effect. So when a current is passing like this, so JC is the current direction. Current is passing like this, and this is a ferromagnetic material in the nearby region. So this is a metal, okay. This is, let's say, platinum or copper or whatever metal, okay. And this is a ferromagnet. This charge current that is passing here, because of the spin Hall effect, and this is again due to spin orbit coupling, as I said, what will happen is the red ones, that means one of the spin will go in this direction, one of the spin will go in this direction. So electron passing like this, because of the ferromagnet that is there on the top, it will, certain kind of spin will go like this, and certain kind of spin will come like this. Okay, so now what is happening is the actual current is passing like this, right? Actual current is passing like this, but some of the electrons which have magnetism in a certain direction, they will go like this, right? So maybe thousands are going like this, maybe 10 of them will go like this. So now what is happening? I'm still able to change it. I'm still able to change the orientation of the free layer. I can change the orientation of the free layer, but without passing a huge current through. Okay, so this method is called the spin orbit torque method. I will show you some practical devices. So this, from now onwards, most of the, because in my PhD I worked on spin orbit torque devices. That's why after this there will be few slides where I will show my own work. Okay, before this they are mostly schematic from other papers, but after this I'll show you some of my own work, and then we will move into the quantum part. So we can take a break if you want to take now, because I think it's already cruel on you. We have started early in the morning in this weather, and you probably, some of you probably missed a cup of tea also. So let's have a cup of tea, and maybe after that, I'm saying cup of tea. I hope there is a cup of tea. Okay. Yeah. So and then we begin again. Okay. All right. So we will. 10 minutes. So after 10 minutes we meet again and we resume this journey. Okay. Thank you everyone.